everybody. It's Monday, May 11th, and this is Nighttime Mathematics Radio. The format of the show is always the same. You tweet your questions into @NightMathRadio on Twitter, and I'll try to answer the questions live on the air. A bunch of questions came by on Twitter earlier asking about sequences, and I'll answer those if nobody else has any questions first. But for now, let's take about a minute back for people to tweet their questions in and try to answer them here live on the air. This is Nighttime Mathematics Radio. Stand by. Welcome back. This is Nighttime Mathematics Radio. Well, we had a bunch of interesting questions come in earlier about sequences and series. This is a topic that starts round about in the middle of pre-calculus and just keeps going. So let's take a look. So we've got a bunch of questions here. Let's take a quick look. First one looks like this. It says, find a formula for the general sequence A sub n of the sequence, assuming the pattern of the first, and it cuts off there. So we'll assume that it has some reasonable pattern after this. So let's take a look at the pattern. Let's go on over. So the sequence looks like this. We have minus 7 thirds, 9 ninths, minus 11 27ths, 13 over 81, minus 15 over 243, and we just have a dot, dot, dot. Now, questions like this are always a little bit obnoxious, because, after all, when all you're given is the first n terms, the sequence could do anything it likes after that. There's nothing that says the sequence has to follow a pattern. And worse, the pattern could be cleverer than the one you spot. But, that said, let's assume that the obvious is going on here. So what do we see? Well, we see three things happening in this series. So let's write as A sub n. The first thing is, you notice the numerator increases by 2 each time. And it starts with 7. So if something increases by 2, that means it has to go like 2 times n. But it's got to be that plus something, because it doesn't just go 2, 4, 6, 8, 10. It starts at 7. So the first term isn't 2, it's 7, so that's 5 more than you'd expect, so 2n plus 5. And we see that works. If you plug in 1, you get 7. If you plug in 2, you get 9. You plug in 3, you get 11, and so on. over. Now in the denominator we have 3, then 9, then 27. So you multiply it by 3 each time. So that means this goes up like an exponential. It goes up like 3 to the n. And finally, the third thing that happens is the sequence switches sign each time. And there's two ways to write that. They work exactly the same way. One is we just put a -1 out front and say it's -1 to the n. Because -1 to the n, after all, switches each time. It starts negative, then becomes positive, then negative, and so on, which is exactly what we see the series doing. Or we can just combine that with the 3 and say a sub n is equal to 2n plus 5 over -3 to the nth power. And either one of those works fine. These are the typical tricks you do with these sorts of series. If you see it increasing by something increasing by the same number each time, that means it's actually multiplying the position. Because if you imagine these things being numbered 1, 2, 3, 4, 5, if something's increasing, you need to multiply that position variable by whatever. If it's increasing by 2, by 2. If it's increasing by 5, or whatever. Then this one, if it doesn't start there, you have to add some extra constant. That's that plus 5. And finally, if you see that something's being multiplied each time, times 3, times 3, times 3, times 3, like you see the denominator's doing here, that means that you have to write it as an exponential. Because after all, this is basically just repeated multiplication. It's multiplied once for the first time, twice for the second time, three times for the third term, and so on. Moreover, if it's alternating in sign, you have to multiply by -1 to that power. Because after all, if you take -1 and multiply it, take it to the position power, it's negative for the first time, because -1 to the first power is -1. It's positive the second time, because -1 squared is 1. Then it becomes negative again, and it just switches each term. And like as I did here, you could combine it with another exponential, if there's another one in the fraction, if there's another one in the expression, or you can just leave it all by itself, and both are correct. Okay. Let's look at another problem from this set. The next one's asking the partial sum -2 plus -4 plus -8 plus ... plus -64 is equal to what? Okay, so how do we do this one? Well, first of all, you can see what each term is. A sub n is equal to -2 to the nth power. And they're all negative here. Just the minus sign isn't inside the exponent. Because these aren't alternating. These are just bang, 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 bang. 2, 4, 8, 16, 32, and so on. So that's what we're being asked to sum. We're being asked, what's the sum of -2 to the nth power from n equals 1 up to, what? 6. So it's 6 terms. There's a few ways we can do this. This is only 6 terms, so we could just directly add them. That will work perfectly well here. So, for example, you could just add these up and say, well, let's see, that's literally -2, -4, -8, -16, -32, -64. So that's -6. You do it by pairs here. -24. 16 plus 8 is 24. -96. So that's, well, gosh, -6 minus 120. So that's -126, and we're done. And that works perfectly well for a problem like this. Now, there's some other approaches to this. This sum, it turns out there's a way to express the partial sum here, which is relatively quick, which you could write down if you want. But for 6 terms, you could just add them, honestly. Okay. Let's take a look at another one. This one's sort of fun. This one says, let me get a new page for this. Rewrite the following as a single sum. We have a sum from k equals 2 to 7, 2k to the 4th minus 6, plus 2 sum from k equals 8 to 12 of k to the 4 minus 3, plus the sum from k equals 2 to 12 of 8. It says rewrite this as a single sum. Well, we've got a big problem here, which is these things all start at different points, which is kind of obnoxious. So we're going to have to do some substitutions. Let's get everything to start at 1 to start with. How can we do that? Well, this one goes from 2 to 7. Let's initially say, let I be equal to k minus 1. Then that's the sum of I equals 1 to 6 of, well, we can rewrite, that's 2 I plus 1 to the 4th minus 6. Now here we have sum from 8 to 12. What's that going to look like? Well, that's... Oh, actually, wait a second. We can be cleverer than this. Let's be cleverer for a second here. Because this goes, rather than rewriting this, let's be clever. This goes from 2 to 7. This goes from 8 to 12. And it's almost the same functional form, you notice. This one has a 2 out front. But we can multiply that 2 into the expression. So this is... So look at that second one. We have, so the first term again was the sum from k is equal to 2 to 7, 2k to the 4 minus 6. This one has a 2 outside, but we can multiply it into the expression, because this is a finite sum. You can always multiply the 2 in. If we multiply this in, this becomes the sum from k is equal to 8 to 12 of 2k to the 4 minus 6. Same thing. So here we've got the sum from 2 to 7. Here we've got the same thing from 8 to 12. Moreover, what happens if we plug 1 in for k? If we plug a 1 in for k, then we have... Well, 2 times 1 minus 6. So we have a minus 4, which is floating around. That's a little unpleasant. But this is a sum from 2 to 12 of 8. Which means, you notice... So let's combine the first two terms first. We have the sum k equals 2 to 7... Sorry, 2 to 12 of 2k to the 4 minus 6. Plus the sum from k is equal to 2 to 12 of 8. So what that means, we could add the 8 to every term. Same thing. So this is the sum from k is equal to 2 to 12 of 2k to the 4 plus 2. So that's cool enough. And notice this is almost the same as what would the sum be if we put a 1 in there? Well, if we put a 1, if there was a 1 term, this would be... So at this point, we've already solved the problem, by the way. This is a sum from k equals 2 to 12 of... This is a single sum, k equals 2 to 12, 2k plus 4. If we wanted to, we could turn this into a sum from 1 to 11 by just doing the substitution I started to do up top. So if the thing forced you to do 1 to something, you could say, well, okay, now I can do what I started to do and say let I equals k minus 1. So then that's the sum from I equals 1 to 11 of 2 times I plus 1 to the 4th plus 2. And then you just expand this out. This is a typical expansion, right? This is a sum from I equals 1 to 11 of 2 times I to the 4th plus 4i cubed plus 6i squared plus 4i plus 1 plus 2. And you could expand this out and there you're done. Or you can just write this down. That's the same thing. And that's how you combine this into a single sum. Okay. And I think that's all the questions that were asked. Okay. So, hopefully the person out there who was asking these questions now has some better idea what to do. Let's take a break again and see if we get any more questions in. So, once again, if you have any questions, tweet them to @NightMathRadio on Twitter. When we come back after the break, we'll answer anything that gets tweeted in, or we'll end the show for the night. This is Nighttime Mathematics Radio. Well, everybody, it's looking like a quiet night out there on Twitter, so I think it's time to end the show. So once again, if you're in this strange world where all the classes have stopped, but the homework goes on and on and on, just come on into Nighttime Mathematics Radio in the evenings, and we'll help you out. Good luck to everyone out there who's going to take the AP Calculus test tomorrow morning. And for tonight, stay safe and keep doing the math. See y'all tomorrow, everybody.